Hey everybody, Dr. A here, and in this video we're going to be exploring an example of how to use Castigliano's method to analyze a frame. So let's go ahead and get started. In the given information, we're being told to use Castigliano's method to compute the slope angle at point C in this frame down here. We're also being told that E is 29,000 KSI and I is 400 inches to the fourth. And we see my battery's running a little low right now, but that's okay. We'll just keep rolling. So how do we get this started? How do we get this ball rolling? Well, the first thing we want to look at in this frame is this is what we sometimes could call a cantilever frame. We have a fixed connection down here at A, and this member from A to B is at a 50-degree angle. Then we have a horizontal member from B to C. Now the diagonal length from A to B is 12 feet and the horizontal length from B to C is 10 feet. And then across BC we have 0.2 KLF of load. All right. Now, since our x coordinates are not defined, we're going to go ahead and define them for ourselves. So I'm going to say, let's call x1 from C to B, and let's call x2 from B to A. That way we can avoid solving for external reactions. We can solve for those external reactions, but why do that when we can just avoid it, all right? The next thing we want to take note of is we have two segments here. We have two domains, so we're probably going to have to do two cut sections, right? So we're going to use the summation version of those integrals when we're applying Castigliano's method. The last thing we want to make a mental note of is if we want the slope angle at C, we're going to need to put a unit couple moment at point C in the expected direction of deformation, which should be in a clockwise fashion right here. All right, so let's go ahead and get started. So I'm going to say solution. And I'm going to say place that that variable couple moment M prime at point C. Okay. If I said unit couple moment earlier, I apologize. It should be variable couple moment M prime. A unit couple moment is what you would use if we were doing virtual work. So place M prime at point C, and to do that, I'm just going to redraw this just so we can visually see what we're doing here. Remember, we keep the real loads there. So this is the 0.2 KLF real load. And then we're going to put that variable couple moment here, M prime. All right. And then, you know, this is still 50 degrees. This is 10 feet long. And then this diagonal length is 12 feet long. All right. Now we're going to use method of sections. All right. So for method of sections, we're going to say cut 1. All right. And cut 1 is going to be from 0 up to, that's x1 up to 10 feet. All right. And so I'm going to draw this free body diagram. I'm going to have this cut here. That is at a distance x1. This is 0.2 KLF. And then, of course, M prime is there. And so we've made this cut here, and we're going to have this internal moment M1 become visible. And, you know, obviously we're going to have a V1 and an N1. N1 will be 0 here. But we're really just interested in M1, okay? So I'm going to say sum of the moments about the cut equals 0, counterclockwise positive. And we just apply our equilibrium equation. We're going to say minus M prime. And then we're going to say minus 0.2 KLF times x1 over 2. And then we're going to say minus M1 equals 0. We'll do a little bit of rearranging, and we'll get M1 is negative 0.1 x1 squared minus M prime. And for Castigliano's method, we're going to need some partial derivatives. So I'm going to say dm1 dm prime is going to be equal to just -1. Remember, when you take a partial derivative, this whole term with the x is treated as a constant, so it zeroes out, and you're just left with this leading coefficient in front of m prime. And that's where we get the -1 from, okay? Now we're going to need to make a second cut. I'm going to scroll on down a little bit, make some room here. We're going to say cut 2. Now, cut 2 is going to be valid from 0, x2, up to 12 feet, okay? So cut 2 is going to be somewhere in this diagonal member, all right? And so by method of sections, how do we draw this? Well, I'm going to draw everything from above here. So this full 10 feet is going to show up here. This is 0.2 KLF. This is 10 feet. And we make this cut here. This is 50 degrees, all right? And we're cutting at a distance x2, all right? And what becomes visible here? Well, of course, we have M2. That's what we're really interested in. And, you know, there's going to be an N2 and a V2 here as well, but we're not as interested in those. For Castigliano's method, we're really just interested in this M2. Now, here's where we have to be careful, okay? We need to, you know, some moments about the cut, of course, right? So we're going to say some of the moments about the cut equals 0. Now, when we do that, oh, what did I forget? Oopsie daisy. Almost forgot one of the most important things, M prime. Okay, now when we sum moments about this cut, what we have to be careful about is we have this angle right here. And the cut is some distance x2 down this diagonal member, all right? And so what we're going to need is a moment arm. In particular, we need a moment arm, a perpendicular distance from where that cut is to the centroid of this uniformly distributed load, okay? So we need this perpendicular distance, okay? I'm going to call this D right here. Now, how do I get D? Well, I'm going to use basic trigonometry here. D is going to be equal to 5 feet plus x2 cosine of 50 degrees. How do I know that? Well, again, this distance right here is 5 feet. That's this 5 feet. What about this little horizontal distance, right? What about the horizontal distance from the cut to the corner of the frame? That's the x2 cosine 50, all right? So it's that diagonal length x2 times the cosine of 50 degrees. That gives me this horizontal distance from the cut up to or over to the corner of that frame. All right, and then I add that to this 5 feet, and that's how I get D. All right, so why is that important? Well, that's going to be a moment arm that we're going to use right now. So looking at this free body, I'm going to say minus 0.2 KLF times 10 feet. That's the length over which it's distributed, times that perpendicular distance, times this distance D right here. All right, so that's going to be 5 feet plus x2 cosine 50 degrees, all right? And then I'm going to say minus M prime, and of course, you know, I've got the minus M2 at the cut equals 0, all right? So if you're a little rusty on your method of sections and your trigonometry, maybe pause the video, rewind it, watch it again, make sure you know where this comes from, all right? We're going to do some rearranging, and we're going to get M2 equals -10 minus 1.286 x2 minus M prime. I just did some algebra rearranging there. And I'm going to get dm2 dm prime to be -1. All right. Now we're ready to set up Castigliano's formula. I'm going to get theta c is the summation as I goes from 1 to 2 of the integral from 0 to L m over ei dm dm prime dx all sub I. And this is going to get expanded into 2 terms. Now, when we substitute in this moment function m here, what do we set equal to 0? We're going to make a note here. We're going to say set m prime equal to 0 in the moment function. All right, so how do we do that? Well, it's pretty simple. We're just going to expand this. Theta c equals, that first domain is 0 to 10 feet, and we're going to say negative 0.1 x1 squared over EI times negative 1 dx1 plus the integral. This is the second domain, 0 to 12 feet, negative 1.28 times x2 minus 10 all over EI times negative 1. That's that partial derivative, dx2, okay? And so we can evaluate these integrals. I evaluated them already. I got 33.33 kip feet squared over EI plus 212.6 kip feet squared over EI. And we can add those together and we get 246 kip feet squared over EI, rotating clockwise because it did come out as positive, right? These partial derivatives that were negative filtered through and flipped the signs and made it all positive, all right? Now we need to substitute in E and I, all right? So we're going to say EI, and we need to convert units accordingly, right? So we're going to say 29,000 KSI, and then I think I was, I'll have to scroll back up and remind myself, 400 inches to the fourth. Okay, so 400 inches to the fourth, and let's crank this through and see what we get. We get a big number, of course. So we get 116, and I got 5 zeros here in my calculator. Okay, and this has units of kip inches to the fourth. All right, now we need to convert that because this numerator has units of kip feet squared, and now the denominator has units of kip inches to the fourth. We see that clearly the kips are going to end up canceling, which is, you know, what we hopefully should expect. I'm sorry, this should be kip inches squared. I think I've been saying that a little incorrectly, kip inches squared. So the kips end up canceling, which makes sense, but we need to convert those inches squared. So we're going to say times 1 foot over 12 inches, and we're going to square that. So we're basically dividing that number by 144, okay? And we get 80,556 kip feet squared. But again, the kips end up canceling, and so you substitute this value into the denominator here, and you should finally end up getting a theta c as the following value. I'm punching this into my calculator in real time. So 0.00305 radians. Okay, notice that you end up with kip feet squared over kip feet squared. So not only did those kips cancel, but the feet squared canceled, right? And so you end up with, it looks like it's unitless, but for an angle, that is radians. Now, if you really wanted degrees, you can multiply that by 180 over pi, and you would get a rotation angle in degrees of 0.1751 degrees, okay? And either of these answers would be correct, but of course, if you had a multiple choice question, like you could see on the FE exam, you want to look for particular units that they may be asking for, okay? Also remember, this is a frame. This is a deformation of a frame, so you don't really have any pre-derived formulas for loaded frames. So if you have a question on any kind of exam, including the FE or the PE exam, and you're asked to calculate some kind of rotation angle or even a deflection or a displacement on a frame, you're going to want to use a method like Castigliano's method, or virtual work would be another good option. Okay, so I hope this video was helpful to you. If you like this video and you like all the content that you find on this channel, please hit like and subscribe. Thanks for watching.